Okay, you may proceed.
All right, thanks, Veyachi. Good morning, everyone. As per the introductions, my name is Orapeleng Mogawana, and today I would like to talk about the work that I did for my MSc, which was titled Meshless Hydrodynamic Simulations of Young Supernova Remnants. So this work was done in collaborations with my then supervisor, Dr. Shazrin Mohammed, and co-supervisor, Dr. Kat van der Hayden. I am at UCT, and I have some affiliations with SAAO too. All right, so in this talk, I would like to cover a couple of things that were motivated for this project. So the motivation was the fact that there is a huge diversity in pre-supernova mass loss rates and circumstellar medium structures. And this comes in terms of how the stars evolve, and these evolution, whether that's in terms of winds or episodic mass loss, there could be an implication in the type of progenitor stars leading up to a supernova explosion. And how we wanted to do this was to run a multi-method simulation approach to kind of model how these interactions from the photospheric explosion up to the 100 years of evolution of supernova remnants, how that evolves and what's the dynamics and the morphology of these. But then in order to do that, you have to actually test your code, and that comes in terms of verifying how your simulations compare to the exact solution to simple problems. And that is very important because how your code behaves tells you more about how you're going to tackle your problem, whether it's applicable to that problem in terms of its astrophysical attributes, and whether it satisfies the conditions for that particular problem. And so in this work, we covered simulations of supernova ejecta interacting with the circumstellar medium. And we have to set up the initial conditions after showing that our code is more applicable to this particular problem. And later on, I will touch on the implications of one of the few red supergiant WOHG64 that has been shown and observed to have some kind of an asymmetric torus of a circumstellar medium structure. So I'm sure most of you in this community are familiar with this picture. So this is the stellar evolution life cycle, or at least the simplified version of it. And the initial mass of stars dictates how those stars are going to evolve and where they end up in their end stages. And I'm mostly concerned with the massive star end of the cut, which is anything that is above 8 solar masses. And even in this arena where massive stars will evolve, go through super red giant phase and go into a supernova or a black hole or any other remnant that results, there's still a plethora of diversity in terms of how different initial masses dictates how that star is going to evolve and how that star is going to explode in a supernova. And in case you are wondering what's that diversity like, this is a type of this is a multi grouping of different stars, at least in the massive end of the cut, where you have different stars, O-type stars, B-type stars, yellow supergiant, red supergiants, and Wolf rays and LBVs, luminous blue variables. And all these will end up as different supernovae. And that is to say, they will evolve differently depending on the initial mass. They will lose mass via stellar winds or eruptions and instabilities. And that type of circumstellar medium structure that is being set up will dictate what type of a remnant the supernova will end up as. And this is something that's really important in the supernova community, because if you know the mass loss rates and how the stars lost its mass during its lifetime, you can track down how it actually lived. So you can actually probe the mass loss and how that star set up the circumstellar medium around it. Again, the diversity is huge, and these progenitor channels, any of these progenitor channels could lead to any of these end stages in collapse supernovae. And the trick is to map how these stars evolve and where they will end up in this variety of supernovae. And just to show you an example of how stars set up their circumstellar environments, this is a Wolf Ray 104 star. So it's been shown here in the radio by ALMA, where you see these dusty rings around a star. And then in another picture here on the right, you can see that this is a pistol star. This is like an LBV star, where you can see like eruptive, unstable mass loss, where a star is losing mass in these episodic pulsations, something similar to this, where you can see all this gas that is being set up around the star. So these, we know that they will end up as supernova because they are more massive, usually at the 40 solar mass cap. And that supernova, the resultant supernova, will interact with the circumstellar medium around it. And how that circumstellar medium is set up will be illuminated by the supernova shock, and it will tell you how the star lived at the end stages of its lifetime. So just to touch on how the supernova ejecta interact with the circumstellar medium here. So at the very end, when the star explodes, the outer envelope of the star, at least the remaining outer envelope of the star, will explode and will be accelerated at really fast velocities, around 30,000 kilometers per second. And when that material slams into this circumstellar medium around it, it will push against the circumstellar medium, and the circumstellar medium will push against the ejecting material, or the ejector in this case. And when that interaction happens, you will have some kind of an interaction region where, in this case, you will have a forward shock that has been formed, where the material, the densities are high, and the material is moving at speeds several times faster than the speed of sound in that medium, at least. And then the reverse shock, where the material has been interacted and collapsed in such a way that you have a boundary of two shocks that accommodate each other. And in the middle, you have some kind of an interaction region where the material from the downstream of the forward shock and the material from the downstream of the reverse shock is mixing, and that mixing it has a lot of turbulence, has a lot of dynamics that's happening in there. You have radio emission coming out of that mixing because of the high temperature material that has been shocked, and a lot of discontinuities and a lot of instabilities in terms of, in this case, mostly related instabilities. And this is really an important region, because what usually happens is when you look at supernova remnants, this is the region where you find most of the emission. Especially the reverse shock, you will find a lot of X-ray emission, and then in the quantum discontinuity and in the downstream material from the forward shock, you see some kind of free emission or radio emission, synchrotron emission. And this is all important if you are going to kind of infer when the material is illuminated by the explosion, how that material was set up, because usually this is not seen in the optical. It's only illuminated during the supernova explosion. And there are two explosions here, the supernova 154 and 1987A. So the most interesting one here is the 1987A, where it's been shown to be expanding. So the material is still expanding after, I think this is after, almost 100 years of expansion, where the shock is cooling and the material around the supernova is being illuminated by the X-ray emission in the reverse shock and in the interaction region. So what has been observed from these regions, mostly radio, there is some X-ray data, but the radio emission is the one that really can be used to map out the structure of the circumstellar medium around these objects. And one of the few supernovae that show these is the 1993J, supernova 1993J, where you have, short wavelength emissions coming out at earlier times in the expansion of the supernova interaction region, and then long wavelength emissions coming later when the shock is cooling and the entire expansion is cooling due to just free expansion. And there's another one which shows some kind of bumps in the radio emission. So this is 1979C, where you see radio emission coming out both in the long wavelength and short wavelengths, but then in the later stage of evolution, you can see these periodic bumps in the radio emission. This has been theorized, and people have suggested that this could be like circumstellar shells that has been set up by how the star lived. Whether this was in the binary situation or episodic mass loss, is still a matter of debate. How materials like this, how the star set up a circumstellar material like that. But nonetheless, it is observed in some of the real observations of radio emissions. So now, for our work, having said that and having understood what's the stake here, which is we see all these remnants, they come in different shapes, different morphologies. How then can we set up a theoretical background and model to say what type of supernova and what type of circumstellar material will set up or will result in a certain type of supernova remnant? And the way we do this is through computational hydrodynamics. And computational hydrodynamics is something that has been here used in science for a long time. But here in astrophysics is rather ubiquitous in a sense that it's now being used to model a whole lot of astrophysical systems. But in this case, we use it to model gases, which is ideal gases in a sense that that is how at least we expect the gas around around stars and circumstellar material to behave. And one way of doing this is to set up the hydrodynamics equations. So these are mostly in derivatives. So you can have equations. These are the equations. So don't be scared of them because they are just the equations that you use to integrate and evolve how gas behave in their hydrodynamic approach. So what you have here is the equation that governs mass and density, and then you have the velocity equation and internal energy equation. And these equations will be dictated or closed by the ideal gas equations that govern what that gas is doing at a particular in that particular environment. And you just put this in a computer, write an incredible code, and make it parallel, and for some with good magic and a really good practice in how you code, you'll get a really incredible fast code that can model any system of gas that you want. And one way of prescribing how you approach this. So there are different prescriptions in hydrodynamics. And one way of doing this, or at least the most traditional way of doing it, is smooth particle hydrodynamics. So here is you choose a particle, and this particle will be your point of interest. And this particle, you will have a particle that has some kind of a smoothing length or a domain, and this domain is associated with how a fluid behaves at that particular position in space and in time. So it's usually Lagrangian, and it's very simple and conservative. You don't have losses in advection and across boundaries as you'd see in the most traditional code of grid codes, for example, that have been used for the same kind of approach. But smooth particle hydrodynamics is such a powerful approach in a sense that all you do is take a bunch of particles, choose your point of interest, and then from those different particles, from a bunch of smoothing particles or a number of neighbor particles that are around that one particle, you can calculate the smooth quantities. So, for example, if you have this particle representing your fluid parcel, then how I would calculate the velocity or density of the particle would be the sense that I would have to calculate the particle within the smoothing length, and that is the particle within the spherical radius around these different particles. So I would calculate the density here, and all these other particles, and then average them all together, and I will get a density from that particular fluid parcel. And this is really interesting because you don't have like I said, losses in an advection where particles have to travel across boundaries, and and especially when it comes to like geometries that deform as we have established in supernova remnants, where gases deform and change shape and stuff like that, then you really do not want to use boundaries to calculate densities and other quantities. But then we also use two meshless methods. Sorry, I did not mention the fact that smooth particle hydrodynamics is a form of meshless method, although it is the predecessor to many other meshless methods. Meshless method is just an umbrella term for hydrodynamic approaches that do not have boundaries in their prescription. And so this is another prescriptions that we have decided to take was the meshless finite volume method and the meshless finite mass methods. So these behave roughly the same as SPH. They have some kind of an established boundaries. Well, it's hypothetical boundaries, and they have a much more, they don't suffer a lot from dissipative effects that smooth particle hydrodynamics suffer from. So we went on and tested those two to model our situation, which is supernova remnant shocks and other in that regime, other quantities in that regime for shocks. So how you do this is usually high performance computing. This cannot be done in your ordinary laptop. It needs a lot of power because you have to track billions of resolution elements in 3D, which is a lot of power and a lot of work. If you were to do this serially, you would spend 1,000 years trying to converge to a solution. And the code that we are using here is Gizmo. So Gizmo is one of many codes that have been written for this, right? And it's one advantage of it is that it has a multi-method approach, and that is to say that you can use different methods within the same code. So if I want to turn on SPH, I can just turn on SPH. If I want to use MLB, if I want to use grid codes, I can use grid codes, which is really easy for testing and verification and knowing which method would be applicable to your particular case, to your particular environment, and how you want that code to behave and how you expect it to behave in that case, in those similar cases. So yes, it is a hybrid MPI, open MPI code. That is just to say that it uses distributed memory and distributed parallel processing, and it takes advantage of the many core computing cluster. And this way you can reduce the compute time to days. This comes at the price, though, of a high power bill, expensive hardware and software licensing. So it's usually deployed in institutions and organizations with the capability of doing these things. So for my case, because we are dealing with supernova remnants and explosions and shocks, the best test that you have to conduct here is the Taylor blast wave test. So the Taylor blast wave test is a test that really dictates what are the shock jump conditions when the shock passes through an ambient medium with constant densities. What will be the solution at the shock jump condition? That is, what will be the solution when the shock passes at the at those particles, how the particles behave in terms of their density, their velocity, temperature, and pressure. And how we do this is set up an initial condition, use an integration code in 3D, in this case, in a spherical domain, to kind of compute the solution, the exact solution, that we know exactly how that looks like because it has been modeled analytically. And in that sense, we started with these type of initial conditions. The energy that we inject is 10 to the power 51 eggs, something in the neighborhood of supernova explosion energy injection. And then there are several other power law exponents that we use, omega 0, upper and lower boundary, desired final time 20 years. So this is chosen, 20 years is chosen as a defining factor because we are modeling the set of Taylor regime of supernova explosion. And that is anywhere between 0 and 100 years. That's where the supernova will spend its set of Taylor phase, and this is just the free expansion phase where the shock is cooling, the material is cooling, and the shock is expanding, and everything is just free expansion. There is no other energy injection or energy removal from the system. It's quite closed and contained. And in this case, we set up our initial ambient density to in the neighborhood of 10 to the power of minus 24 grams per cubic centimeter. That is, again, some assumption on the diffuse nature of circumstellar mediums around stars, especially when you are around from 0.1 to 0.5 parsec around from the photosphere of the star towards the outer region or where the circumstellar medium starts. And the initial velocity, assuming that the circumstellar medium is not moving, temperature, pressure, you have pressure being dictated by what density that was given the ideal equation of state, and then you have to define the sound speed or the speed of sound in the material given how your specific heat ratio is given. So if you are dealing with more, in this case, we are dealing with 3 degrees of freedom. So that will dictate how your initial sound speed is in that material, in that medium. And then, this specific internal energy, again, is dictated by the ideal gas equation of state. And then on the right, you'll see the exact solution for all the quantities: density, velocity, temperature, and pressure. And the shock jump conditions that we talk about are these giant peaks here, where you have the material that is unshocked, the shock itself, and the downstream material that has been shocked. And these conditions are the ones that are really important in understanding, because they are really difficult to model in systems, especially like with SPH and other codes. So you have to get these exact solution. You have to know that your code is doing exactly what it's supposed to do. Otherwise, your code, when you model your system, it won't be representative of the shock conditions. And so that being said, we went on a testing spree. So that is to test many other things that the code can do, just to make sure that we eliminate all the possible cases that the code is not working. In that case, trying to by ourselves converge to a setup and parameter space in which the code will work. So we tested gravity among particles. We tested artificial viscosity. So this is a term that really tells you how, especially in shocks. So in shocks, you will have when when you have shocks passing through a material, artificial viscosity is important in dampening down the dissipative effects of SPH and the treatment of shocks. So this is another term that we had to test and see how that works. Another one was artificial conductivity. This is all about mixing, how particles mix with each other, both the upstream and downstream particle and at the shock position itself. This is all being tested in SPH. So these are all SPH testing parameters. And then going to MFV, meshless finite volume and meshless finite mass method, we had to test the number of neighbors. So by convention, number of neighbors is how many particles you have around the particle that you want to compute your gas quantities for. And the more quantities you have, the more you converge to the right solution or the right gas quantity. So if you increase this number of neighbor value and you use higher order kernels, that is to say, the functions that dictate how you compute those gas quantities, then by convention, you should be able to get a more accurate solution for your gas quantities. So we went on to test all these and many other aspects of the code. And the representation of how this looks like would be something like this. So for the gravity test, we tested everything for gravity, gravity amongst the particles themselves. And this showed us at least that MFV is by far at least the most superior when it comes to capturing the shock when you have gravity off, but this is only in density space. And when you might think that, okay, all the codes are behaving well, they are doing what they are expected for the shock jump density. But then when you go to velocity, you end up with a couple of them that diverge from the solution. And one of them is actually, one of them is actually SPH with gravity, with self-gravity enabled, where it mostly diverges from the solution in velocity space. So another one is other quantities like internal energy and pressure. And what I want to bring to your attention here is the fact that although MFV seems to be working well here with gravity off, when you get to specific internal energy and pressure, you will have this giant discontinuity that goes below the ambient medium, and it diverges from the solution. And this is not what to be used, right? That already tells you that you should not be using MFV with gravity off, because it won't be applicable for this particular case. So this is why testing these codes is very important before you just applying it for your models. And we went on to test different smoothing channels with a number of neighbors. This is for each and for SPH, MFV, and MFM methods. Again, the ones, and you can see a pattern here, the ones with bigger kernels with more number of neighbors seems to have the edge in terms of how they approximate the shock jump conditions. The shock jump condition says that it should be at least 4 times the ambient medium, but as you can see, the code itself is still struggling because of the smoothing conditions that's being applied, the smoothing kernels that's being applied. The shock has been broadened a bit at the shock jump conditions. So the more of a higher kernel you apply, in this case, say you have SPH with M6 kernel with 128 number of neighbors compared to M4 kernel with 57 number of neighbors. There's the blue curve. And then you will see that the density here is much lower than the density in the lower kernel. So that means because you're using more number of neighbors in a bigger kernel, the smoothing function is even more rigorous, and you kind of have this broad shock structure. But then what you lose in broadening, I think you gain in the position of the shock, which is another thing that should be taken into account. For if the position of the shock was here after 20 years, then you will have a problem. So it's important that your position in the peak of the shock are exactly as predicted by the exact solution. And another quantity that we tested, artificial viscosity and artificial conductivity. Again, these are the terms that are artificial conductivity, the one that tells you how the fluid behave and take care of the dissipative downstream particles, which is things that are usually here. And then artificial conductivity, things that are inside the shock where the mixing is happening, right? And we wanted to test this because when you go to, I can just jump back to this. When you go to velocity, mostly this is the dissipation that happens when you have a lot of unstable fluid flows and a lot of errors in how the fluid is supposed to behave. And the artificial conductivity and artificial viscosity can give you some kind of conversion in this solution to know that at least the downstream particles are behaving as expected. So, so after testing all this, we looked at many other, another prescription of artificial viscosity, the Cullen and Delhen artificial viscosity prescription and the Balsara switch artificial viscosity prescription. These are just artificial conductivity terms. And at first look, you might realize that, oh, actually the Balsara switch is much, much better than any other ones that we have tested up to this far. And particularly the Balsara switch with no artificial conductivity, right? It's working really well. Well, I will tell you later why this is not the case when we are doing the symmetry test. And then we also did the resolution test. So this is to check whether your solution converges, whether the more particles you use, the more compute power you use, and the more number of neighbors you use, will you be able to converge towards an absolute solution? And for all of the codes that we tested, it seems like that's the case. When you go from 500,000 particles to 10 million particles, you can see that the solution converges towards the source. So with more compute power, you should be able to approximate the to get the shock jump conditions exactly. And these were done just for, so these were done just to make sure that if we model our solution, our problem, we are able to say that, okay, these particular parameters under these conditions will converge to a solution, and we can be able to use more and more particles to get better results. It should be noted that for SPH, I'm using the Colloquium switch. So this is the artificial viscosity and artificial conductivity terms that are used in that are suggested in Gizmo. They have their own paradigm themselves. There's a huge arena where these things are being tested, these terms are being tested. So we don't really cover the scope of artificial viscosity and artificial conductivity that much here. But then we just wanted a parameter space that actually works for this case. So, so here's the cross-sectional plots of density. So this is because you are modeling these things in 3D. So I'm taking a cross-section slice at the center of my 3D box. So the explosion happens in a 3-dimensional box, in the center of the 3-dimensional box, and then I let it evolve for 20 years. And then after that, I take density across that at the center of the 3D box. So that is at around 3 parsec. And then just try to check how is the density distributed from the center towards the outer boundaries at that position, right? And here on the left, you will see these density cross sections. The right color, this right color diagram represents the log density, and then these are just XY positions in parsec. And then you can see that when we're using the SPH with artificial conductivity and artificial viscosity, you have a slightly symmetric, expansion. And then you come to B, where we're using the traditional Balsara sheets, the one that had a better shock jump densities. It's actually a little bit asymmetric, and the shock is not as smooth as you expect it to be. So if your code does not satisfy this condition, then that means the expansion itself is not smooth around the shock. So materials are moving at different velocities, whereas in the shock itself, you expect all the material to be moving all at the same time, at the same velocity. But here, because of this, unstable shock expansion, it's not really ideal for our modeling purposes. And then this is for MFV and MFM, and as you can see, they are behaving really, really well when it comes to symmetry, and that has been shown in other quantities too, where they actually capture the shock and have a lot, and they are very robust in actually capturing shocks and modeling the shock jump conditions. Another one that I wanted to show was the pressure quantity. That was a density quantity, again, log pressure, cross-section pressure plot. And as you can see, the SPH with Cullen and Dallin switch, artificial conductivity and viscosity switch, still has that symmetric shock, whereas the Balsara switch is really not stable around the shock. And then the two MFM and MFV codes are behaving really well in this sense. So in this testing, what we have found out is that SPH is better at resolving shocks at the position of the shock. MFM and MFV are slightly a little bit off, around 0.01 parsec off if the conversion is right. Well, in no 0.01 code units of so, and then this is prevalent in other SPH quantities. The most prevalent thing is the fact that the shock will be broadened as opposed to something like grid codes or MFM and MFV. So there's nothing that you can do, is the way the code has been set up. And MFM and MFV handles the downstream particles better. That, if you remember, that's the particles that have been shocked. So there isn't a lot of dissipation in that. The pressure and velocity don't suffer from oscillations as evident in SPH. So that's the velocity profile that I showed you earlier with a lot of oscillations. In MFM and MFV, they kind of follow the solution, although they still struggle in the downstream all the way to the P0, position 0. So MFM and MFV still have like a really sharp shocks as compared to SPH because of their broadening and smoothing kernels treatment. So that being said, we now have to set up our model and set up our model and our initial conditions for simulating the actual interaction of the supernova ejector with the circumstellar medium. And how we do this is have to set up the initial conditions. So we do this in two parts. The ejector, which is the envelope that is expanded during the explosion. So that is sent into the surrounding circumstellar medium. So remember, the star explodes, the outer envelope of the star blows apart, and that becomes the ejector expanding into the circumstellar medium. So this is done as a piecewise function. The first one is the core, which is rather flat in free expansion, and the other one is the intermediate region where the density exponentially decays, so that is all the way to the edge of the leading ejector shock, and then density 0 for anything that is greater for velocities that are at the maximum. And then for velocity, you have velocity, anything that is smaller than the radius of the ejector. You have velocity that is in free expansion. So this is just a material that's moving in free expansion. And then anything that is greater than the radius of the ejector, you have velocity that is 0. So you have this profile here. So we set this up in 3D in a spherical sense, particles all over, in kind of consecutive shells where you start with this part, the flat profile, and then you have consecutive shells of particles that have been set up to represent the ejector profile. And then now we have to set up the circumstellar material, the circumstellar medium of it. It too has the initial conditions. And this is done with the 1/r² profile. So the assumption is around red supergiants, you will have circumstellar material dropping, circumstellar density material dropping in a 1/r² profile. So the further you are from the internal boundary of the circumstellar material, the less density you will encounter. So that's the case. So you can see that in here where you start off with a kind of higher density and then you drop with 1/r² profile. And then the velocity, you set it up in such a way that it's zero, the material is not moving, and other quantities like energy, where you have the material of the circumstellar medium having a larger ambient energy, and then this one, the energy, this is just the ambient energy of the ejector. But then as soon as it starts moving with the injection of kinetic energy, then you will have an ejector that is moving at a really high expansion rate. And then the pressure will follow the density initial condition setup. And then the other model that we had was the Taurus model that is inspired by the paper of the asymmetric torus that I'm going to discover later, where you have discuss later, where you have the bipolar cavity and the torus around the star that has been set up with a dusty torus and kind of an opening angle where the gas is set up in a 1/r² profile, and yet you still have this torus structure. And this is where what we wanted to test, and how will the resulting remnant look like, whether it will be observable. We'll see these as asymmetries. And we started with simple models, really. 2D simulations are the best way to see how the code behaves, or at least what to expect, and whether this is what we want to see in 3-dimensional scenario. So this is 1/r². You can see the density is dropping as you move away. The ejector at 20 years, the ejector at 100 years. And this is the density cross section again, taking the slice through the center of our simulation box. And you can see the ejector in free expansion. And then you have the reverse shock. So that's this continuous boundary that's separating the reverse shock from this contact contact discontinuity region, where you have this mixing of Taylor instabilities. You have the circumstellar material, the forward shock, which is the moving shock that was encountered during when the ejector slammed into circumstellar material. And this is representative of what we expect. Although we had a problem with these bubbles that started forming, that's just the code artifacts. We tried to investigate this. It did not really pan to give a solution of how to get rid of them. So we contacted the author, and it is something that is inherent to the code and not the way we set up our initial conditions, because in other 3-dimensional case, this is not really prevalent. So the idea here was to model the asymmetric torus model of WOHG64, inspired by the paper by Onaga 2008. So this model assumes a sphere of a biconical cavity. The density drops from the torus to the bipolar cavity along the longitudinal direction. And the real density distribution is assumed to be 1/r². And then it corresponds to like the steady mass outflow with constant velocity. And this is the artist's impression of how the star would look like in its super-red giant phase as it's losing mass. And then these equations are the ones that dictate the density distribution, the temperature distribution, and the mass loss rates parameters of the system itself. So we set up this initial condition. As you can see, the ejector in the middle, the Taurus model, with the density changing from the Taurus to the biconical cavity at this 60 degrees angle, and then you have the mass fraction of between the density and the biconical cavity to be 0.03, and then mass loss rates typical of supergiants, and then density variations between maximum and minimum from the internal to the outer edge. And after all that, and then allowing the simulation to to evolve, we end up with something like this, a morphology of a supernova that expands at 20 years, where it's really hard to tell. Still looks really spherical after 20 years of explosion of evolution. But then you go up to 100 years in free expansion, you start to see the material in the cavity moving much faster because of the lower densities in the cavity itself, and the material in the torus moving a little bit slower compared to the material in the cavity. And that's why you see the shock a little bit bulging out and this oblate shape of the remnant. And this is shown across all the fluid quantities, instabilities everywhere in temperature space and velocity space. And so this is the resulting remnant that you would see if you were to observe this kind of system. And here we do the projection plot along the z-axis, and this is taking the column density along the z-axis and then projecting them to see how this would be observable in terms of the emission that's coming out of it. All right, let's say you would have an optical observation of this remnant, then you would see if you were to look at it from the xz plane, so depending on the inclination of how you are observing, you most definitely see this plumes of material coming out of the biconical cavity, and the bleeding shock in the torus still being recessed compared to the biconical cavity. But in a sense, you still have the spherical profile, so it wouldn't really affect the asymmetry in a sense, because if you allow this to evolve much further into 200 and 1,000 years, then the material in the torus would catch up to the material in the biconical cavity, and you still have that spherical symmetry. If you were to observe it in the XY position, so that's face on, then you only see the material in the biconical cavity expanding towards you, and then that would just look like a spherical supernova that has occurred. And
Orapeleng, I'm sorry just to bother you a bit. So we are over the top of the hour. So we actually committed to everyone for an hour. So if you could bit quicker, so that we have to have some time for questionnaires as well.
Yeah, okay. So this is definitely the last slide. Yeah. So that being said, we kind of inferred that the remnant of WOHG64 SNR would have visible asymmetries if it was to be observed, and this would depend on the inclination angle in which you observe it, as per simulations have proven. So it's a kind of hit or miss situations, whether stars like this, if you were to observe them, then part of them would be still a Taurus model, but then they wouldn't, when you observe them, you wouldn't really get the asymmetric profile or asymmetric morphology that is represented here. So yeah, this is where the journey ends. And like I would like to say that in most cases, we can only have models that are useful, and that we only can approximate based on what we observe. And most of the cases, the data that comes from observation will dictate how models look like. And yes, thank you for listening. And yeah, I'm all for questions.
Thank you, Orapeleng. Thanks for the talk. Anybody have questions? I don't see anything on the chat. So if you guys have a question, Patricia, you want to go ahead?
Yeah, thanks very much. It's a very interesting work, Orapeleng. One of the examples of a real massive star that you showed at the beginning of your talk was WR 104 with the spiral structure. And I think we understand that that spiral structure is formed by binary interaction, and binaries will be relatively common in these massive stars. If not binaries, then planetary systems, possibly massive planets. I mean, obviously that's beyond the work that you've done here, but do you have any sense of whether the blast wave will just go past the planet or the binary star, or is that going to make a fundamental difference in the way that the expansion of the supernova goes?
Yes, precisely. So depending on the initial injection of the star. So for example, like you said, the Wolf-Rayet stars, so they are expected to have like high initial masses, which means the compact star that explodes, so that in the carbon star or whichever star that's going to explode, the envelope will need a lot of energy injection and to drive that material out into the circumstellar medium. And if there is a binary there, I'm not quite aware of any surviving remnant of a compact object that survives the explosion next to a star. But when the ejector slams into that circumstellar material, you will have some kind of emission during, like especially in radio, like I showed earlier in my. Let me see. So this is suspected to have been having a spiral circumstellar medium, right? And this is a potential result of what the emission would look like if the ejector itself slams into a spiral type structure circumstellar medium, because this episodic drop is showing in densities, because the flux density, according to Chevalier model, is related to the density of the circumstellar medium, or the density distribution of the circumstellar medium. So when it slams into the spiral circumstellar medium, you have a density flux density increase in the spiral itself, where the material is compact, and as soon as that spiral, as soon as you hit some kind of a cavity, then the flux density drops, and then it increases again following this periodic flux density variations. So yeah, that's really something that has been shown in the radio light curves and has been observed before. But I'm not quite sure whether the binary star system itself, whether the companion star will survive that, whether that would be a compact object or just another main sequence star.
Thanks.
All right. So we have another raised hand from Camelo.
Hi, thank you. Yeah, first of all, I wanted to congratulate Orapeleng on giving a brilliant presentation. Just have just a minor question. I don't know if it's probably something that I missed on your SPH model before you started looking at the CSM. Were you still assuming you were modeling a red giant, or what mass of this, or what stellar mass were you modeling with that study?
Sorry, can you repeat that? Your video audio is a little bit low in my side.
Okay, sorry, let me try to increase. Hopefully I'm more audible now.
Yes, you're audible now.
Okay. Yeah, I was saying that before you included the CSM on your models, on your SPH models, were you still modeling a red giant? And what stellar mass did you assume in that model of that study that you were doing?
For SPH, you mean when I was doing testing?
Yeah.
Oh, so for testing, I wasn't really including anything that has to do with the models. I was modeling the exact solutions. So the exact solutions is the solution that we already know. So this is the analytical solution that you already know of how shocks will behave under certain gases, right? And I was only assuming the parameters that are representative of the circumstellar medium. So, for example, I wasn't doing the 1 over r squared density dropped from inside to the outside. I was just taking the constant density to see how will the density change when the shock passes through it. If I know the exact solution to that, then when I take those parameters and put them back into my exact models of 1 over r squared and the Taurus model, then I know that it's actually behaving as it's supposed to. So I was only taking parameters that are representative of the gas itself and how the astrophysical gas is, but I was not really including that into I was not really including the shape and the morphology and the setup of the circumstellar medium in the test itself, because that means that you are altering the exact solution, and I wanted to test the exact solution, whether the code does what it's supposed to do.
All right, thank you. That makes sense.
All right. I don't see any other questions as of now. Anyone else? Yeah, I have a very basic question. So what's the advantages or disadvantages of meshless over mesh grid simulation?
You mean what's the advantages of meshless versus grid simulations?
Yeah.
Okay. So that both of them have advantages and disadvantages, right? And advantages of meshless mostly is their conservative property. So how they conserve mass from one interaction to another. Whereas grid simulations, they use boundaries to calculate how much mass has passed from one region to another. And that, when you have a lot of contorting and changing shape within the simulation itself, that is to say for example, you're modeling something. For example, for my case, I had Rayleigh-Taylor instabilities that are changing and having swirls and eddies and really unstable fluid flows. Then the accuracy in advection, which is what grid codes use, is really off, because what it's going to do is going to change the shape of the fluid parcels, going to change the shape of the grid itself, and that can have a preferred calculations in a certain directions and certain direction, or in a certain because it's a grid, then you have calculations occurring when I are occurring across boundaries, or when the boundaries are contorting and changing, then you have some preferred directions of where densities clump and under densities occur. So that's not a really good thing when you have environments where things are changing, advecting, and you have turbulence, which is another interesting property that makes it difficult for grid codes to actually capture. So that's one thing. I will say one thing, that grid codes are actually good at capturing shocks, but then you are not really interested in just capturing shocks. You want the best parameter space that's going to tell you how your code behaves, and that way you can get the best of everything, because it's one thing to know how to capture shocks, but it's quite another when your code is too dissipative and the fluid is not behaving as it's supposed to when it comes to other fluid quantities. So there's advantages and disadvantages. Like I said, SPH has a lot of disadvantages when it comes to the using the kernel. Everything is all broadened up. Quantities are not sharp. You don't have like the direct measurements. You have only broadened averages of measurements. So that can be a hindrance in calculations that you use. But you have to just decide after a lot of testing, of course, like I did, to get the right amount of parameter space for the particular code that you're using.
Okay, thank you. I don't see any other questions, so let's everyone give a round of applause for Orapeleng for the nice seminar. And thank you everyone for joining. We will adjourn the session now. Bye-bye.
All right, thanks everyone.